Hello. Today we're going to talk about Topic 4, Section 18, Population Tests. All right, so when collecting sample data, it's better to have multiple samples, right? And make your samples as large as possible, right? Of course, that's usually easier said than done. So what does that mean? All right, when this happens, how much can we infer about the population with what we've just sampled? Okay, so that's when approximation comes into play. So approximation in data can help you approach the truth, but unavoidable errors may keep you from being able to achieve the truth. Okay, let's do an example. So we know what the standard deviation is known, the population standard deviation. Okay, so that's first type of example we're going to do. So Li Wei is a peanut farmer in southern China. After harvesting his peanuts, he packages them in 25 kilogram bags, all right, and ships them off. So, of course, he gets a complaint that says, hey, I didn't get what I bought, so now he's got to investigate. Okay, so he takes a sample of 6 bags. Well, he notices that 4 of the bags weigh less than 25, and the mean sample is less than 25. So is that enough evidence to say, hey, my company's messed up? All right, I gotta fix this. All right, is it enough to say he's got a problem? So what do we do first? There you go. Name your null and alternative hypothesis. That's what they're called. Sorry. All right, a little slip in the brain there. Okay, so we want to say that our mean is 25. All right, our alternative hypothesis, we're testing to see if it's less than 25. Because really, if it's more than 25, it's, I mean, yeah, the company's probably taking a loss, but it's not really a big deal, right? I'm still doing what I advertise. And the problem is they're challenging my advertising, okay? So here, if the weights of the sample, it has a standard deviation of 1.5 kilograms. I'm sorry, of the population has a standard deviation. Calculate the p-value. So how do we calculate that? We do a t-test. I'm sorry, a z-test. The z-test is when we know the standard deviation. So we go to our calculator. That would be under, let's see, oh, there you go, stat over tests, and then we're going to z-test. So we know our information, so we're going to use statistics. Just kidding, that's not this one. We have the data, so we've got to use data, which means I've got to input the 6 samples into list 1. So then once you do your list, you would put your mean as 25, your standard deviation, in this case, the population was 1.5, that was given to us. It would be our list. And then here, we would do a one-tailed, the left side, and then we would hit calculate. I didn't put the list in there, so I can't hit calculate, but what should pop out is this number. So that's a 33.2% chance might have a mean weight of this. Okay, so there's a 33% chance of collecting a random sample have a mean weight of that or less. So what does that mean? Since that is more than 0.05, right, a 5% level of significance, we don't have enough evidence to reject the null. Okay, so we don't have enough evidence to conclude that the weight of the bags is less than the required 25 kilograms. Okay. All right, it's not rare enough. Think of it like that. All right, so now to find, given the standard deviation, all right, calculate the critical region for a test using a 5% significant level on the sample data. All right, so it is normally distributed. So here is our mean and our variance. So we plug in that. Notice that the mean is rounded here. I believe the average of this was, what, 24.73 repeating? Okay. Let's see. Once you plug that into your calculator, right, doing your inverse norm function, okay, the probability is 5%, is less. Let me say that again. The probability of leeway sample mean, the sample average being 23.99 or less, is 5% when the sample size is 6, right? We did a 6 sample size. Okay? All right. So the critical region would be less than 23.99. Okay, so example 3. So we have a candy company. All right, they claim they put 60 candies in each package with a standard deviation of 5. They want to know if it's actually 60. So they select 20 packages and find the average to be 57.1. What's the null and alternative hypothesis? Well, all right, the null is that it equals 60. All right, the alternative is that the mean does not equal 60. We didn't care whether or not it was more or less. There wasn't a complaint. There wasn't someone happy, right? We don't know the difference. Or we weren't inspecting for a certain reason. We just want to make sure, all right, we just want to see what it is. We just want to make sure that it is 60. So we calculate the p-value and determine whether it's sufficient evidence to reject the null hypothesis at a 1% significance level. So we run a z-test since we know the information, but this time we do statistics. So this is our population, and this is our sample with 20 items. That's our alternative hypothesis. All we need to know is how to put it in our calculator. We calculate it, we get a p-value. That's what we look at. So based on that p-value, all right, there is a 0.949, so less than 1% chance that a random sample of 20 packages would have a sample mean of 57.1. Okay, that is a very, very small chance. So there's enough evidence to reject the null hypothesis, okay, since it's less than 0.01, less than 1%. Therefore, an employee can report to the company that machine is not filling packages with a mean of 60 candies. Okay. Okay, again, it would be very unlikely to have a sample like this. So the odds that I got it should put up some red flags. So that means I need to do some more investigation. Think of it like that, okay? The odds of this sample happening is a very, very slim chance, less than 1%. So it's very significant. So we gotta alert people. All right, so now let's do some examples when the population standard deviation is not known, okay? When it's not known, we do a t distribution. Okay, so we don't know, okay, we're waiting for someone to spill the tea, all right, so we're doing a t distribution. I know, that was pretty lame, but I'm tired and that's all I got. So, the mean length of time it takes for a certain roller coaster is 54 seconds. Blah, 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 blah. So, state the null and alternative hypothesis. Oh. Okay, I forgot where I hit it. It's over here. Okay, so the null hypothesis is that it equals 54, so the mean time is 54 seconds. The alternative hypothesis, all right, is that it's less than 54. Okay, so calculate the p-value. So we're going to use a t-test. So inputting that information into our calculator just like this, we can get a p-value of 0.145. So we can, since that is more than 10%, we can fail to reject the null hypothesis. This does not mean that you should accept the null hypothesis, okay? Just understand that it's, I know, it's words, okay. What this means is, all right, this is not significant enough, so it's pretty likely that this is okay, so we think that the mean is 54. We don't have enough information to reject it, but there's so many possibilities, there's so many outcomes, there's so many reasons that I got the information that I got. So as statisticians, we never want to say for sure. We never want to say this is it. So that's why we say we fail to reject, okay, as opposed to accept, all right? Okay, so now let's talk about matched pairs. So look at two different trials we have here. So weight loss, all right, you have your before and your after. If we just look at the average of the before and the average of the after, it looks like, well, in both these trials, it looks like people lost weight, okay? Roughly 2 kilograms, okay? So, all right, sounds good, right? But let's think about it, okay? Look at your data, especially in trial number 2. The first person, well, they lost 30 pounds. That's awesome. But look at the last person. They gained, oh, I said pounds, I mean kilograms. So this last person gained 30 kilograms. So really when I did averages, they kind of canceled each other out. And so when we are comparing things like this, like the same person before and after kind of thing, we want to do a matched pairs experiment. All right, that's because it's just, it can showcase those differences as opposed to just doing the overall average. All right, because it's not taking that into account. Okay, it's just a better way to look at the data. All right, so let's do an example. So here we have, let's take the weights of the first trial. All right, and let's find the difference between the before and after weight. Okay, so we find the differences. We plug that into our calculator as list 1. All right, because here we want to see if choosing a 10% significance level, all right, we want to show that this exercise program effectively helped the participants. So we want this difference to be 0. Okay, right? That would be the null hypothesis with saying that there would be not helpful, right? There's no difference. Okay, we want that mean to be less than 0. Right, we want that difference to be less than 0, all right, because we want it to be less of a difference, right, losing weight, right? We're going to do a t-test, all right, we get a p-value of this. So, sorry, get rid of those dots. Okay, so here we get 0.08, that is less than 10%, so that is pretty significant to get some kind of results like these. So we can reject the null hypothesis and say that the mean is less than 0, so therefore people are losing weight. So this is good program, right? We didn't say how much they were losing, but they're losing it. All right, now let's look at example 2, all right, in comparison. So here we find the difference between those values. All right, we state our hypotheses and do it at a 10% significance level. So we run a t-test. This time we get 0.40, so 40% chance, all right? So we can we do not reject the null hypothesis, so it looks like there isn't a difference, okay? So this is not showing that people are losing weight. Okay, so see how the difference is? If we just looked at the averages alone, we would have claimed both trials were good. But when we run these t-tests, we get much better data when we subtract the the differences. We do a matched pairs. All right. All right, so now we're going to use binomial probability. All right, so remember binomial, you just have those two outcomes. So here, if the p-value falls within the critical region, then the test suggests that the population's proportion is different than the one stated, okay, than the original. So some things you want to remember, that successive events must be independent of each other for binomial. You'll only be expected to carry out the one-tailed test, and remember that it measures the counts of an outcome. So how many times something happens, okay? All right, so, and you always want to make sure that it comprises of integer values, so none of those decimals. All right, so let's do an example. Okay, so looking at the first example, the drug company says 76% of their patients reduces back pain. We get 20 patients. 12 of them say they have they reduce their back pain. So getting out our calculator, we want to go to Binomial Cdf. I do this every single time. All right, so Binomial Cdf is here. Let's see. We did 20 trials. We have the probability of no back pain is 76%, so 0.76. And we had 12 patients. So what does that mean? Oh, I got to hit enter. So 0.08. So interpreting that, here's our null hypothesis. Our alternative hypothesis would be less than 76% of patients, right? Because that would be bad. Here, we get 0.08. That's less than 10%. So we can reject the null hypothesis and accept the alternative. All right, since it's less, we reject it. Accept the other one, saying that that we have less than 76% of people getting a reduction of back pain. So that's not good. Okay. All right, let's do example 2. Okay, so for example 2, all right, 2% are defective, and let's see, we want to sample 75. So how many would I have to get defective to have an issue, right? That 5% significance level. So let's see, your null and an alternative hypothesis would be this, okay, stating exactly 2% are defective, more than 2% are defective, okay? So we could just plug in our binomial CDF and make up an X value, right? 1 light bulb defected, 2, 3, 4, 5, right? And you could keep getting your values. Okay, I don't know. You could do it this way. I liked the calculator, so I prefer to graph it. So I used the binomial CDF, and we had 75 trials, 0.02 for a defect, and we have X number of trials. Then I adjusted my table, and I started at 1, and I went up every 1 because I'm counting the number of defects, and then I just looked at my table. So then here, I'm able to see when I hit 95%, all right, is got to be at least 4 defective light bulbs. Okay. Wait, they had 5. Oh, I forgot about the 2 tails. Okay, so 5% would be 2.5% on each side. So 2.5% would get you to 4 to 5. Okay, so we're going to choose 5, okay, if we contain 5 or more defective bulbs, then the null hypothesis rejected, and we can conclude it's now greater than 2%, so we've got a problem. Okay, so if in our sample, if we've got 5 or more, we have an issue. All right, so let's test the mean using the Poisson distribution. So remember, that's a binomial distribution, so you're counting and there's an infinite number of possible outcomes, right? I can keep going on and on and on. So here, the station or the train passes the station every 10 minutes. So we measure it in 1 hour and count 324 people. So we're expecting it to be greater than 50 for one 10-minute span, right? 50 people waiting for a train. So after 1 hour, we would expect 6 times 50, so 300. So our null hypothesis is when it equals 50, the alternative is that it would be greater than 50, right? That's when we know we have to speed up the trains. So we want it, what we have, is 324. So we're looking at when it's greater than 324, right? So alternatively, you do 1 minus, because you're always doing the left side, of 323, right? Because you're counting, you're not doing those decimals. Okay, so you plug that into your calculator using the the Poisson distribution, the CDF. So here we would expect 300, but what we've got is 324. Oh, I'm sorry. 323, because this is doing the left side. Okay, and that's where I got the 0.911 from. Then do 1 minus that, and that's the greater than 324. Okay, so that's not sufficient evidence to reject the null. Okay, so we fail to reject the null. So it's good. Okay, so let's find the critical value for that last one. So I would go to my calculator and I would plug in the Poisson CDF, and now the X value would just be X. Okay, so then now my table set is going to start at, let's see, 300. I think that was our expected, or 324. Isn't that our last answer? Okay, it doesn't matter. Let's just start it. So let's look at our table. That takes a second. All right, so those of you visual. All right, this is our null and alternative hypothesis. So we can just plug in random stuff into our CDF, just, plugging in one after another, or using the table set. So here, when you get down to 327, yep, I'm gonna just keep on chugging. So once you get down to 330, that's the big difference. So at 329, you're at that 95%. So here you are looking at 330, right? Because you would do 1 minus, and that would be at less than 5%. So 330 people. Okay, don't mistakenly put 329. Okay, because that wouldn't pass the it would just give you the wrong critical value. It would be the wrong percentage. Because remember, you'd have to do 1 minus 328, and that would give you greater than 5%. So you gotta watch your numbers there. All right, so when we're testing population correlation, that's fun to say. All right, we follow it similar to that linear correlation, right? So if p equals 0, there's no correlation. If it's greater than 1, it's positive. Greater than 0 and positive correlation, less than 0, negative correlation. Okay? Let's start with an example. Okay, so here we've got the correlation coefficient for the data. All right, we want to know whether there's sufficient evidence at the 5% significant level to reject the null hypothesis for p equals 0. Okay, so the null hypothesis, the alternative hypothesis, we use a linear regression t-test, all right, because we don't know the population statistics, all right, and since it's less than 0.05, there is sufficient evidence to reject the null hypothesis, that there's no correlation. All right, so it's important to understand that when there is sufficient evidence to reject the null hypothesis, okay, so in this case, then it's appropriate to calculate the least squares regression line, okay, so that there is some kind of relationship between the two, correlation. All right, so for example 2, so we have 2 people that are measuring the reaction time. All right, so we want to determine whether there's a positive correlation between the 2 sets of data, and if there is, determine the least squares regression line. So here, well, I guess I kind of gave it away. All right, so your null and alternative hypothesis. All right, since we're testing for a positive correlation, we want p to be greater than 0. So p equaling 0 is no relationship. All right, we do our linear regression t-test. We get 0.00595. Therefore, it is smaller than 0.05, so there is enough evidence to reject this one. So state that there is some type of relationship. So therefore, we can do the least squares regression line. Okay, and again, we ran the linear regression t-test. Gosh, my handwriting is bad. Whatever, you get the idea. Okay, so there are 2 different types of errors that you can make, okay, when it comes to this null and alternative stuff. So here, most of the time you can see it in a easy to remember chart, right? They don't give this to you, so this is what you want to remember. So this is what happens in reality, and this is what happens in your study. So obviously the green, everything's great, okay? Everything came out perfect. However, bad things could possibly happen. So you could have a type 1 error where in reality it's negative, but the study said that it was positive. Okay, and type 2 would be the opposite of that. So how do you remember? Well, there's this really, really cute cartoon that someone made. To me, I really like it, so I highly recommend you watch it. Another example I saw someone gave me before is type 1 error is like telling a man that he's pregnant. Okay, obviously, reality, he's not pregnant, but my study said he was. Okay, so think of it like that. A type 2 error would be like telling a, 8-month pregnant woman who's got this, big old round belly that she's not pregnant. That's a type 2 error. Okay, think of it like that. Obviously, that's not, that's just one generic way to remember it. Okay? All right, as always, let's do some examples. So with a type 1 error. All right, so going back to our light bulb problem, okay, remember that we found that the critical value was 5. Okay, so we need to remember that. So our null hypothesis and our alternative hypothesis. And so considering the case of 5 defective light bulbs. So what's the probability of getting more than 5 defective light bulbs, because that would have caused a problem. If I had found more than 5, then I would have more than 0.2%, I'm sorry, more than 2% light bulbs being defective. So I have to do 1 minus the probability of getting 4. So when I do that, I get 0.0173. So the probability of that happening is 0.0173. So the likelihood of making a type 1 error is 1.73. That's not the same as the significant level. Don't think it is. Okay, so we had the probability based on getting more defective light bulbs. You have to follow the context of the problem is what I'm getting at. All right, if I confuse you, please talk to me in class. All right, let's do another example. So going back to the train problem. Okay, considering the critical value, what's the probability of making a type 2 error? Okay, so you want to remember your null and alternative hypothesis, right? We cared if it was more than 300 because then we would have to adjust the train schedule. So using that information, we found that at 329, it didn't make the 5% significance level, but at 330 it did. So we want to keep it less than or equal to 329 because it will be rejected. The null hypothesis, hold on, let me get my words together. Okay, that the null hypothesis will not be rejected for values less than or equal to 329. So we don't reject it when it's, greater than 5%. So at 329 or less. But I will reject it if it's greater than 330, because then now I'm less than 5%. Okay, now remember a type 2 error is, go back to it, type 2 error, it's positive in reality, but I said it was negative. Okay, so it actually happened, so that means we want it to be, we want to not reject the null hypothesis, so we want it to have less than 329. So find the probability that it's less than 329, and we get 0.385. So there's a 38.5% chance of this being good, but I could mark that, I could say that no, it didn't happen, right? So that's a type 2 error. Okay, so if the mean number of people waiting over the course of 1 hour is 335, okay, they get 335. I'm just confusing myself. Okay. I'm so silly. That's the mean number of people is 335. There's too many numbers going around. Okay. So if the mean number of people is 335, then there is a 38.5% chance that the sample will not give the subway authority reason to increase the number of trains. Okay. Again, I hope that makes sense. All right, this is all you need to know for this subtopic. I know it was a long one. It's over 30 minutes. Had a lot of info in there. Okay, I tried to do all the examples that I could. If you are stuck, you need any more help, please contact me. All right? Y'all take it easy.